Hello, welcome to my channel. In this video I'm gonna take another practice exercise problem from chapter 3, practice exercise problem 3.7. So the problem is we have to determine flux of a vector field rho square cos square phi a rho plus z sin phi a phi, which is in the cylindrical coordinate system. So we have to determine the flux of this vector field over the closed surface of a cylinder, which has z from 0 to 1, rho is equals to 4, and we have to determine the flux, and at the same time we have to verify the divergence theorem for this case. So this is a new term, divergence theorem. So we are gonna first define the divergence theorem, explain it, and then go to the problem solving part. In my previous practice exercise problem solving video, I discussed about divergence of a vector. The divergence of a vector measures the outward flux of a vector field. s- uh, uh, for example, a fluid, outward flux of a fluid or a outward flux of a gas from a point uh, in uh, in all directions through a surface per unit volume. So now from this divergence concept, the concept of divergence, there's a corresponding theorem. So the corresponding theorem is called the divergence theorem, which states that the total outward flow from that designated point of a vector, say vector field A, if the outward flow is through a surface which is enclosed, then the integral of the vector field through the closed surface can also be represented by volume integral of the divergence of the vector field. So in summary, the outward flux of a vector field can be expressed by the volume integral of the divergence of that vector field. So now let's get to the practice problem and solve it, and it will be more easier to in action it will be more easier to understand the divergence theorem by solving problems. Let's get to the problem solving part. So this is the given vector field. So and we have to find the um, flux. We have to find the flux of this field over a closed cylindrical surface. So say this is our cylindrical surface. So the flux from the cylindrical surface can come out from the upper side, which is pl- which is in the positive az direction. The flux can come out from the bottom of the cylinder, which is minus az direction, and the sides, and from the sides. So for closed surface, and the cylinder has the ranges 0 to 1, rho equals 4. Flux say phi, which is the integral of the vector through the whole closed surface. So let us um, um, let us um, divide the surfaces of the cylinder by, say, the top surface is T, the bottom surface, and the sides. So small s, this is bigger s. So so we are gonna find the total flux of the closed surface, the cylinder, in partitions. So let us first find the total flux from the upper surface of the cylinder. So in the upper surface, um, the differential surface is rho d rho d phi in the direction az. So for which differentiation in the top ds is, this is in the direction az, but the vector field has no z component, so this is obviously 0. So d rho, so there is no flux from the upper surface, so this is 0. Also from the bottom surface, the differential surface of the bottom side is also d rho d phi, but in this case minus az. So bottom surface has, so double integral, and because the vector field doesn't have any z component, it will be 0. So the bottom surface also has no flux through the uh, through the surface. Now for the differential surface through the sides of the closed cylinder has differential surface rho d phi dz in the direction arrow. So the sides ds will give us, so it has the component rho square cos square phi rho d phi dz. Z is 0 to 1, and phi is, we can see that phi is from 0 to 2 pi, it is spreading like this. So this is phi, so phi is spreading like the full circle, so 0 to 2 pi. If we just calculate this, so rho cube, so rho cube and cos square phi d phi 0 to 2 pi, 0 to 1 dz rho cube from the trigonometric uh, formulas. So 2 pi 1 plus cos 2 phi d phi 0 to 1 dz. So rho cube phi 0 to 2 pi plus sine 2 phi by 2, so there's a half. So half 0 to 2 pi and z 0 to 1. This will give us, so rho is 4, so 4 cube cross half 2 pi plus sine 4 pi is 0, so this is obviously 0 and cross 1. This will give us 64 pi. Now what we're gonna do is we're gonna calculate total flux from the closed cylindrical surface. So say total flux is this, so top dds plus flux from the bottom dds plus the sides of this closed cylinder dds. So because the vector field has no z component, so in the direction az, the top surface and the bottom surface doesn't have any flux through the top and bottom surfaces, so 0 plus 0, and from the sides the vector field emanates the flux 64 pi. So this is the total flux emanating from the closed cylinder. Now we have to verify this result. We have to verify this result um, from the divergence theorem. So let us first take the divergence of this vector. So because this is in cylindrical coordinate system, 1 by rho del rho rho d rho plus 1 by rho partial differentiation with respect to phi d phi plus partial differentiation with respect to z dz. Now the d rho component is this, so 1 by rho del rho rho cube cos square phi plus 1 by rho partial differentiation, so phi component is z sin phi and there is no z component, so partial differentiation 0. So partial differentiation with respect to rho of this component is 3 rho square cos square phi plus 1 by rho partial differentiation gives z cos phi which is 3 rho cos square phi 3 rho cos square phi plus 1 by z sine, sorry, 1 by rho z cos phi. So by divergence theorem we know that the surface integral of a vector through a closed surface can be expressed as volume integral of the divergence of that vector over a volume. So this is the divergence theorem. So now we have found our divergence for this vector. Now we just have to take the volume integral. So volume integral divergence of the vector d dv. So differential volume in cylindrical form is rho d rho d phi dz. Volume has no direction obviously, so v 3 rho cos square phi so this has come to this. Now 3 0 to 4 rho squared d rho 0 to 2 pi. So range of the phi for a cylinder is 2 pi, 0 to 2 pi. It can rotate from 0 to 2 pi. So 0 to 2 pi cos square phi d phi 0 to 1 dz plus 1 by rho d rho 0 to 4 plus, sorry, cross 0 to 2 pi cos phi d phi 0 to 1 z dz. Now so yeah, 3 cross rho cube by 3 0 to 4 cross, in the previous section we found this, so 1 plus cos 2 phi half 0 to 2 pi, and this is z 0 to 1 plus this is rho 0 to 4 cross sin phi 0 to 2 pi cross z square by 2 0 to 1. So this gives us the answer. So 3 cut out, so 4 cube, and in the previous section this is cross 1 by 2, this is phi plus sine 2 pi by 2. So this is 2 pi, obviously. um, Phi from 0 to 2 pi, so 2 pi, and sine 4 pi is 0, and sine 0 is 0 obviously, so plus 0, and then 0 to 1, so 1. And here rho 0 to 4 cross sine pi, sine phi, so sine 0 is 0, sine 2 pi is also 0. Thus this whole term becomes 0, so plus 0, so this will give us 64 pi, thus proving our solution. So this is proved by divergence theorem. So that's it. I hope you understood my explanations and the calculation, and thank you for watching thus far.